Okay, let's do a quick recap before we continue forward. So, regression analysis, the basis of it is that we make an assumption. We assume that y has a linear relationship with x. So y could be, let's say, income, right? And x could be anything like that we believe has a relationship has a relationship with income, right? Maybe education, right? And so the goal of this is to use x to predict. Use x to predict y. Now, whenever we make a statement like this, has a linear relationship, what we're really saying mathematically is that I can express y and x in this form. Right? Now, what's this epsilon I? Right? This is the residual. So anything that obviously there are other factors to income other than education. Right? There are hundreds of variables, and that is all included in this. Right? Now, when we say relationship, there are three types. They're either beta 1 could be 0. Beta 1 could be greater than 0, and beta 1 could be less than 0. Right? So beta 1 equals 0, that means there is no relationship, right? Meaning x doesn't affect y. Beta 1 greater than 0, that means it's a positive relationship. Beta 1 less than 0 is a negative relationship. Right? And visually, right, this is what we want to understand. We have y and x. Right, have scatter plot like so, right? And what our goal is to get this line, right? This line here, right? It is what we call the regression line, right? Or the regression equation, right? This is beta naught plus beta 1 xi, so no epsilon, right? And so this and the difference between the observation and this expected value, this regression equation, that's our epsilon, right? Okay, and the idea to think about is that not everybody with the same education has the same income, right? So we have that error there. Okay, now our regression equation, that's this line here, right? Let me just write it again. The expected value of yi equals beta naught plus beta 1 xi, and this is what we want to estimate. Right? Our goal. Right, we want to estimate beta naught and beta 1. Right? These are the population parameters. Okay, similar to mu. Right? Similar to how for the whole semester we've been estimating mu, and then here we want to estimate these two. Now there are hundreds of ways to estimate population parameters. There is no one right way, right? All of them are completely valid. However, there are some ways are better than others, and the least square method, this is the one we've learned in the past handout, right? That's the best method. Now, if you continue to study statistics, right, then you will understand why that is the best method. But for now, just take my word for it. The least square method is the best method. Now, how do we calculate these estimators? Oh, so to estimate beta naught, we use B0. Okay. Calculation is very simple. It's y bar minus b1 times x bar. So then we'll need to calculate b1 first. Okay, so b1 is this. Okay. Note these are estimators. All estimators are random variable. So b naught and b1 are random variables. That's thing to keep in mind. All right, and 2, they are unbiased. So what does it mean? That means expected value of b0 must equal beta naught. Right? Unbiased estimators means that the expected value of the estimator equals to the parameters we are trying to estimate. Okay, same thing for b1. Okay, so they must equals the population parameters. Okay, now we also say, okay, well, so we have a model, right? And our model is just this linear, this linear model. We want a way to measure how good our model is, right? How well did X help explain Y? Okay? And so first, so we develop criteria called coefficient of determination. Okay, and so again, this is the picture you want. And here we have y hat I, which is b0 plus b1 xi. So this is our predicted value. Okay, this is our prediction. Okay, and then we still have our observation. Right, these are our sample. Right? These are our sample here, and so this is basically our prediction error. Right, our notation we use is EI. Okay, right. So we're able to explain, right, part of this observation with this equation, but there are still parts that we did not explain. Okay, so let's gather those up, right? And that will be our criteria. So our EI, right, is simply yi minus y hat I, right? So our prediction error, right, equals to our observation minus the predicted value. Okay. This prediction error, another name for this is the residual. Right, what's left over, right, that has not been explained yet. Okay, and then our first measure or metric is called SSE, right, the sum of squared error. Okay, what is SSE? It is exactly as the name suggests. Right, it's the sum of the error squared. Right, and we gather this up. Now, intuitively, right, you want to think that obviously, right, a good model will minimize, right, will minimize this, right, because if I can find a line that minimizes the distance, right, of this from every observation, right, that will indicate a good model. Okay. Now, how should we interpret the sum of square errors? Right? These are the remaining deviations that has not been explained by X. Right? Okay. Now, what are these deviations? Right? These are they come from the SST. So SST is yi minus y bar. So remember, this is our benchmark. Right? This SST represents the total deviation, right, from mean. Right? Okay, I should write that. So that's the total deviation from the mean. Okay, and this is where we begun. So we have this explains the total deviation. We added x, right, and x partially explains some of the deviation. This SSE is the deviation that's unexplained. Right? So SST equals SSE, the unexplained, plus this other term which we will call SSR. Right? So SST is the total, SSE is the unexplained, therefore SSR, right, is the explained. Right? And then finally, right, once we have all these parts, right, we can calculate our coefficient of determination. So that's R squared. Right? And R squared equals SSR divided by SST. Okay? So this is our coefficient of determination, and this will be our measure for our model, how good our model is. Right? And intuitively, this should make sense. Right? You want the deviation explained, right, to be as large as possible. And so this R squared, right, represents the proportion of the deviation explained.